Hey guys, welcome to your second chapter 5 video. This is still on numerical descriptions of quantitative distributions. Last time we talked about the 5-number summary. We looked at the min, the max, the quartile 1, the median, and the quartile 3, with Q1, the median, and Q3 dividing our distribution into 4 separate sections. Bottom 25%, the 25th through 50th percent of the data, 50th through 75th percent of the data, and then the 75th through the 100th percent, that's odd to say, of the data. All right, so today we're going to look at a second way to quantitatively or numerically describe these same sorts of distributions we've been looking at that we'll see in histograms. And we're going to look at the mean and the standard deviation today, and paired with the standard deviation, very closely related, is the variance. The 5-number summary gave us descriptions of distributions which were resistant to outliers. The mean and the standard deviation are a separate, paired set of statistics to describe distributions, and they do not work so well when you have outliers. But the benefit of the mean and the standard deviation, and you will see this as we go through the notes, is that the mean and the standard deviation take all the data values into account, unlike, say, the median, quartile 1, and quartile 3, which don't care about what's above and below them. They just want to know the place in line. Just like if you were in elementary school lined up at the door for recess, what place are you in line? The mean and the standard deviation care about where everyone is in line. Okay. So as we mentioned last class, the median is a great measure of the center of our data so long as our data is skewed. If our data is more symmetric than skewed, however, a better statistic of the center of the sample data is the mean, which you have interacted with before. We don't call it the average in this class because average is sort of a catch-all term to refer to either the mean or the median. Formally, the mean is calculated as follows. We say that the mean is x bar. X bar the x refers to all the data values with the variable represented by x. So if you are, x could be the height of students in a statistics class. So x bar is just going to be the statistic computing that mean. And that is equal to, sigma stands for the sum of all I data values. If you are the first data value, that would be x sub 1. If you are the last data value, that would be x sub n, where n is the number of data values in your data set. And we divide through by n. So it's just an average that you would have taken in middle school. But again, we call it the mean, not the average. Written out a little bit more exhaustively, that will be the x sub 1 plus x sub 2 plus, on up the line, let's see, I'll do this, x sub n minus 1. Nope, I won't do all that. I'll just do this up to x sub n divided through by n. So you add up all the data values and you divide through by the number that you've got. No sweat. That's the average that you've seen before. The median you've also seen before. Hence, we don't call both averages. We've got different names for each of them. Let's see. So with this, let's write this out. X sub I is defined as being that equal sign with the additional dash means this is a definition. The ith data value in the data set. And n will, I'm trying to think of a case where this is not true. N is always, in this class, the number of data values in the set, in the data set. Okay. All right. Let's check out how the mean and the median differ with these two. We've got a pair of histograms here on the left, and then just a solitary one up to the right. In the first pair of histograms, the one on the left, right here, we've got a symmetric unimodal distribution. And in this particular case, the mean and the median overlap because with the symmetry that's going on, the median exists where obviously you've got 50% of the data to either side, so it makes sense that it would be here. The mean exists in that same place because when you've got a high data value over here, it is averaged out with, or excuse me, a low, I said that backwards. Let me re-highlight. When you've got a low data value over here, that would be averaged out with a high data value over here. Hence, the mean and median coexist in that same spot. All right, second histogram to the right, now you've got the distribution that is not symmetric, it's right skewed. The median has not moved much from where the mode was. Notice the mode in the first histogram would also be where the mean and the median are. The mode in this second histogram, second distribution at least, is still where that central peak is. Median was pulled just a little bit to the right because we're, again, just trying to see where 50% of the area is to the left and to the right of some vertical slash through our data. But the median, because it takes into account, look back up here at the sigma x sub I, we average up all the data values. These high data values over here had a lot of what's called leverage on the mean, and they pull the mean further from the median. That is the fundamental reason why the mean is not a statistic measuring the center of our data that is resistant to outliers, while the median is a central statistic that is resistant to outliers. The median doesn't seem to be pulled as much. Similarly, for this last distribution, you've got a distribution that's left skewed here. The mode is marked. The median is pulled a little bit to the left, but not nearly so much as the mean because of these outliers over here. Or maybe we wouldn't call them outliers, but the extreme low values that you've got to the left side of the distribution. Again, and the means again being pulled because it's an average of everything in the data set. The median doesn't care about everything, it just cares about where the halfway point in line is. All right. So with this next histogram, let's see, I don't think, okay, so we're going to basically talk about how you can visualize where the mean would be. The mean is actually marked already for you, and that's a faint line. Let me make that clear. I know that the YouTube videos are not super high resolution. The mean's marked for you right there. The median, if you look at the heights of these bins, your first bin has a frequency of 20, so there are 20 data values in that first bin. Second bin has a frequency of 10, so there are 30 data values in the first two bins. Then the third bin right here going across, just giving you a reference with that arrow. Third bin is at about, not quite, but about 5 for a frequency. The fourth is also about 5, so there's 10 data values. The third is more like at 7, so there's about 17 data values. And going across the last few here, you've got another 4 or so, so 21 data values. So the median would actually be, with this dotted line, somewhere through there perhaps. Median, dotted, the mean is the solid line, okay? So even here too, you've got a little bit of a disparity, a little bit of a difference between the median and the mean. Well, we have said before that the median is wherever you can cut the distribution, so you've got 50% of the data to either side. The mean, however, is the fulcrum, where you would place a fulcrum if the data was, say, basically on a seesaw and you wanted to balance the data. So just like with a typical seesaw, if you want to make sure that, let's say you've got fulcrum of the seesaw here, and you want to make sure that this is balanced. I've got about the same width to either side of the seesaw here, okay? Let's say that those are the same two widths. Well, obviously, we are not going to balance the distribution if you've got big dude over here on the left opposite teeny tiny girl over here, okay? The only way that that fulcrum is going to be balanced is if you've got big dude coming in a little bit, quite a lot, if he's as big as I first drew him, so that he's not exerting quite as much force on that left side. So we want these two forces right here and right here to be equal. And they would be equal if that bigger clump of the distribution were closer to the fulcrum. Similarly for the mean here, where it was marked you've got a big clump of the distribution directly to the left, that your big dude's directly to the left. Then you've got less data to the right-hand side. But it exerts the same force to the right-hand side as it does to the left because this lighter weight data, so to speak, to the right of the fulcrum, which is your mean, is further from the fulcrum. So the seesaw is balanced. I don't think, so all that being said, I think it's important to recognize that the mean can be visualized in that way. It's where you would place the fulcrum if the data were basically on a seesaw. But I don't think that that's going to be something that you will need to visualize often. That's harder to visualize where the mean should be placed than is the median. Because to find the median, like we did at the beginning of these notes, or not the beginning of the notes, but the beginning of this slide, all we did is basically count, okay, we had 20 data values here, 10 here, blah, 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 go across, and find where you've got half the data values to either side. So the median, the dotted vertical line, easy to find visually. Mean, maybe not so much. So I don't think that this is as useful a tool as the vertical slash for the median. But there's that. We've connected it to the histogram. We've connected the mean to the histogram. All right, so just as the mean is great for measuring the center of our sample data when our data is more symmetric than skewed, i.e. think about which would be a better choice here. Obviously the median and the mean were close, but that median's getting, the mean is getting pulled further to the right because that distance that some of those bends are from everything else, the right skewedness that you had going on. So just as the mean is great for measuring the center of our sample data when our data is more symmetric than skewed, the standard deviation is a great measure of spread when our data is more or less symmetric. Remember, with the 5-number summary, you had 2 things that were spread related that you could report. First, and the easier of the 2 perhaps to find, although with the calculator it's trivialized, is the range. That is just, again, maximum data value you've got minus the minimum data value. And also with the 5-number summary, you could get the interquartile range, which tells you the span of the middle 50% clustering of the data. Not where it exists on the number line, remember, but just how far apart the 25th percentile and the 75th percentile data values are. All right, standard deviation is a great measure of spread when our data is more or less symmetric. Intuitively, the spread of the data set is the distance all of our data values are from the center of the data. So like the mean, the standard deviation is going to take into account all of the data values, not just a select few like the interquartile range does. Thus, it might be tempting to create a standard deviation equation as follows. So you might want to think, oh, okay, it's going to look something like the mean, S standing for sample standard deviation. You will see in this chapter just one calculation for standard deviation. Here in a bit, you will see a second that is very closely related to S. The only difference really is the denominator. So, okay, we might think for ourselves that S should be the following. Our first data value, subtract it, subtract the mean into that. That tells you how far the first data value is from the center as measured by the mean. Add to that your second data value, x sub 2, minus the mean, and you just go on up the line until you've hit the second to last data value, x sub n minus 1, where n is the number of data values in your set, minus the mean, plus, last but not least, x sub n minus x bar, or the mean, all divided through by n. So you might be tempted to think, well, that should be our standard deviation, because for each one of these sets of parentheses here, this difference is giving us how far the data value is from the mean. So you just add those differences up, divide through by n, and that fraction would tell us how far the data values tend to be from the center. Well, the problem with that, and some of you guys might see this problem already, just from me having written that, is let's look at a sample data set here. We've got the following. Let's look at 2, 2, 2, 4, 6, 6, and 6. Okay, let's first make note of what the mean is. So x bar is equal to the sum of all the data values. Writing it out just for the sake of illustration here. plus 6 plus 6. Some of you guys will be able to see what the mean is without writing any of this. Divide through by the number of data values you've got. It should come out to be 4. Okay. So if we were to calculate the standard deviation from this with that lowercase s standing for sample standard deviation, this would be equal to 2 minus 4. Oh, I want more room. I'm going to put this below a little bit. S would be equal to 2 minus 4 plus 2 minus 4 plus 2 minus 4 plus 4 minus 4 plus, let's see if I can fit these in, 6 minus 4 plus 6 minus 4 plus 6 minus 4, parentheses, 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 all through here, okay? Divide through by the 7 data values you've got. Well, notice here that these differences, which I'll write in red, you get a negative 2, which you're adding to negative 2, which you're adding to negative 2, no problem so far. Then you get a 0, then a positive 2, positive 2, positive 2. So basically your numerator would cancel in this case, and you would just be left with a standard deviation of 0. Well, that's clearly not meaningful because we know, looking at these 7 data values, that they are spread apart from each other. Maybe not a whole lot, but it doesn't make any intuitive sense to say that there is 0 spread from the center of the data for this data set. So that's why this intuitive equation that I've set up in red would not work. Instead, we calculate the standard deviation as follows. We correct for the fact that high data values and low data values can cancel each other, as we saw in red, marked above the numerator there, by squaring, then taking the square root. So the true standard deviation formula for a sample, and treat that as the only equation we've got at this point. We'll see the second one in a couple of chapters. Would look as follows. The square root of sigma, again meaning the sum of all these things, x sub I minus x bar squared over n minus 1. So it looks similar to, let's make a visual comparison here real quick. It looks similar to the formula we saw last slide, in the sense, well, it doesn't yet. Let me write some more. Let me change my mind on that. That would be equal to, written out a little bit longer, the square root of x sub 1 minus x sub I squared plus, then that you could do that for the second, x sub 2 minus x sub, I said x sub I, x bar squared, plus on up down the line until you have your last data value, x sub n minus x bar squared, and you divide through by n minus 1. So the only change that we're making from last slide with that original equation that we wrote in red is that to account for negative and positive differences from the mean, you square all of these differences right here, okay, and then take the square root. In the process of squaring those differences, you'll get all positive numbers that you will add together in your numerator. And that will keep the standard deviation from ever being 0. Technically, yes, it could be. If you had a data set of, for example, 4, 4, and 4, the x bar, the mean here would be 4, and the standard deviation would still be 0. But that would be an appropriate measure of spread in that case. If all the data were 4, you would want this sample standard deviation to be 0 because they all exist at the same place. So under that rare situation, it could happen. But you wouldn't see, if you use this formula to calculate the standard deviation for the data set 2224666, you would not get a sample standard deviation of 0. It would report positive spread from the center, from the mean. Okay, very closely related to the sample standard deviation is the variance, which is calculated as follows. We say that is s squared. We denote it with s squared, and that is just simply the sum of all the differences between the data values from the mean, x sub I minus x bar squared over n minus 1. So the relationship, if you look at the first line and the second line, the relationship between s and s squared, you take your sample standard deviation, you square it, you get your s squared. Or in reverse, if you've got s squared, you take the square root of that to get s. Okay? So one is the square of the other is the square root of the one. Variance is an easier calculation because you're not taking the square root of all of these. Oh, excuse me. You're not taking the square root of all these added square differences. You're just leaving that calculation without the square root. But the problem, and the reason we use standard deviation instead of variance, is that if you were, for instance, measuring the height of students in a classroom in inches, well, if we were using the variance formula, you would have your s squared, your variance would be equal to the sum of someone's height in inches. Let's say that it's 72 minus, let's say, the mean for the class is 65. When you square that, this is inches. Let me write that out a little bit further. 72 inches minus 65 inches. Square that. Divide through by n minus 1, the number of data values you've got. Well, that gives you inches squared in your numerator. And that's a weird interpretation of spread. If you're measuring someone's height, you want to know how far people's heights tend to be from the mean, which that would be measured in inches. Inches squared has no intuitive meaning for spread in that particular case. So the units for variance would be inches squared. I think that's probably a confusing way to explain the difference here. Bottom line, we use standard deviation because it helps out with making sense of units. Okay, bottom here. Notice that just like with the range and the IQR, larger standard deviations indicate that our data is generally spread farther from the mean than is true for data samples with smaller standard deviations. Okay, so what does that mean? Well, we will, at the end of these notes, we will make sense of that. If this last paragraph doesn't make sense just yet, just hold off with me. Okay, so we've discussed the statistics. IQR, the interquartile range, the median, the mean, the standard deviation, all as tools for discussing the center and spread of a data set. Here's a recap of the rules you should observe when trying to report center and spread of a data set. If the data is skewed left or right, you report the median and the IQR as part of the 5-number summary. Well, the IQR is not part of the 5-number summary, but it's derived from the 5-number summary. So for skewed histograms, the 5-number summary with IQR is the way to go. If the data is essentially symmetric, you would want to use the mean and the standard deviation on account of the fact that the mean and standard deviation use all of the data to calculate the center and spread. The median and IQR, again, do not. And last, if you report data that has an outlier with the mean and standard deviation, report the mean and standard deviation 2 times in your description of the distribution. You will report the mean and standard deviation once with the outlier, and then you will say what the data appears to look like without the outlier in place. So if you've got a histogram that looks something like this, you've got centrally located data right there, then off to the side you've got this little baby outlier. You would, if for some reason, and in this particular case, you don't have skewed data, you just have an outlier, you would want to say, well, I mean, the data set is more or less symmetric. Through here, you're seeing basically the same thing up to the left and the right. You would report mean and standard deviation, or to use the notation we'll see more frequently, x bar and s, but then you also report x bar and s with the outlier out of the data set. Okay? So you would, easiest way to do that, in one variable stats, you've got, if you want to find the mean and the standard deviation for a data set, you can go to one variable stats. After you've entered your data into a list, you would hit, if I remember correctly, it's going to look like 1 var stats, and then if your data is in L1, you'll hit L1, It'll give you some output, and in that output, the two things that you'd want to pay attention to is there is an X bar, which is your mean for the data, and then for the standard deviation, it looks like this. Capital S sub X, the standard deviation of the data, is your that is your standard deviation of the data, rather. Standard deviation right here. So you would do this. You would go through this procedure of entering one var stats from stat calc. It's in the stat calc menu. Entering in your data list right here. It give you the mean and standard deviation. Then you'd go back to stat edit. You would delete the data value that was an outlier and do this one more time, entering in one var stats for that same list. Giving you it would give you a new mean and a new standard deviation without that outlier in the list. All right, and that gives you a reference. The reason that you do that, the double reporting, is that this outlier over here, we know from the discussion we had on leverage in the histogram in the second slide of these notes, we know that that outlier is going to have some significance upon the mean and the standard deviation because they take into account all the data values. So you do double reporting. All right, example 1, find the standard deviation of the data below. Let me erase this stuff right here. I think it'll be enough space. No, let's just take it all so it's not a distraction. Does it not do that anymore? There we go. Okay. All right, so find the standard deviation of the data below. This, again, can be found from one var stats in the list that you choose, but helpful to see it worked out one time, just to make sense of what's going on. So S is equal to the sum of sigma, all of these differences between the data values and the mean of the data set squared, divided through by n minus 1, and we take the square root of all that. So this would look like the following. The square root of first data value is 1 minus the mean of this set is 0.8. You could get that by adding them up, dividing through by 5. You'd square this plus 8 minus 0.8 squared plus, I'm going to run out of room again, minus negative 2 minus 0.8 squared plus, and so on and so forth. You'd have a 3 minus 0.8 squared and a 0 minus 0.8 squared added into that numerator, divided through by, notice that it's n minus 1. I don't know that I want to explain why that is just yet. When we get to the second calculation for standard deviation, which is very closely related to this, I'll talk about it more then. Just take for granted the fact that it's almost divided through by the number of data values in the set, but not quite. It's not worth explaining at this point. Divided through by, instead of 5, n minus 1 would give us 4. Square root of all that nonsense, this would come out to be 3.808. And we don't have units here because the numbers don't have any units tied to them. We're just looking at some numbers. No, we're not sure what these are a quantity of. Let's see. With that standard deviation, that tells us that this is how you would interpret the standard deviation. The standard deviation suggests that, in general, the data tends to be about 3.808 units from the mean, which is 0.8. Okay, so that's how far the data tends to be spread from the mean. That is not the sort of interpretation we could get from the interquartile range. Remember, the interquartile range is what's the span of the middle 50%. Standard deviation is how far does the data tend to be from the center of the data as measured by the mean. All right, so example 2 here, for each of the pairs of data sets in A through C, determine which set of data must have the higher standard deviation. I feel like I skipped something. That was the 5th slide. Oh, yes, I did. In this slide here, there was one other thing I wanted to mention. You are told that when your data is skewed to go with the median and the IQR for measures of center and spread, you are told if the data is symmetric to use the mean and the standard deviation as measures of center and spread. Notice that there are histograms that you could draw, and I kind of drew one already, that will not necessarily be symmetric or skewed. So this is not, as you'll see again and again in statistics, I've not given you a hard and fast rule that will correctly diagnose any problem you've got in your statistics book. Those are guidelines for any rule that I would present to you in determining how you would report or describe a histogram. I can guarantee you that there's a counterexample to it. So take 1 and 2 with a grain of salt. Again, this course is so different than any other math course you've had. You got a feel for how to report the data. Stick to those as best you can, but rules will be broken. All right, example 2. For each of the pairs of data sets in A through C, determine which set of data must have the higher standard deviation. Well, to do that, we first need to know where the mean is. You could add up these data values and check for yourself, but X bar is right here at 6 for the first set of 5 data values. X bar is at 6 for the second set of 5 data values. We know the standard deviation is a measure of how far the data values tend to be from that mean. So rather than calculating the standard deviation by hand, let's take note of the fact that 5 is 1 unit away from the mean, 7 is 1 unit away from the mean, 3 is 3 units away from the mean, and 9 is 3 units away from the mean, giving us some relative sense of what the standard deviation might look like. For the second data set here, X bar is 6 as well. Well, 4 and 8 are both 2 units from the mean. 2 and 10 are 4 units from the mean. So you can tell doing a comparison, pair the 3 with the 2, the 5 with the 4, the 7 with the 8, the 9 with the 10. And all of those pairings, the second data set is further from its mean than the first data set is from its mean. So I've circled the second data set would have the higher standard deviation here. It would, again, standard deviation being how far data values tend to be from the mean. All right, B here, we've got 10, 14, 15, 16, 20. Okay, so mean, first data set is 15 as well. You could calculate that by hand if you want to, or maybe you can see that. X bar is 15 for the second as well. So let's do the same thing again. How far are the data values from that point? Well, you've got 5, 1, 1, and 5. You've got 5, 4, 4, and 5. Okay, pair the 10 with the 10, the 14 with the 11, the 16 with the 19, and the 20s together, and you can see that the 10 and the 10 paired with the 10, the 20 paired with the 20, they are the same distance from their means. But 14 with 11, 16 with 19, it's clear that this second data set, once again, tends to be further from its mean than the first data set. So again, the second data set would have a higher standard deviation. Last one here, I don't think you can necessarily, well, maybe you can. If you can, awesome. The mean here is at 8 for the first data set. The mean here for the second is at 88. So distances, comparing those again, you've got distances from the mean of 6, 2, 2, 1, 3, and 6. For the second data set, 6, 2, 2, 1, 3, 6. Okay, so which would have the higher standard deviation? Well, neither. They would be the same. You can't really circle either of these data sets because even though the second data set is a set of higher numbers, they still tend to be spread just as far from their mean as the first data set is spread from its mean. So neither standard deviation would be greater than the other.